Yes, it's MK the guy. Today let's talk about cephalosporins. Previously we looked at penicillins. We saw penicillin as one of the class of lactam antibiotics. Today it's cephalosporins. So we are going to talk about a brief history of cephalosporins, nomenclature, semi-synthetic derivatives, chemical degradation of cephalosporins, parental cephalosporins, spectrum of activity, beta-lactamase resistance, and pseudomonas cephalosporins, generation, side effects, and esters. Please don't forget to like the video, subscribe, and share. So let's begin with the history. In 1945, the guy called Cephalosporins discovered that the cache of Cephalosporin acremonium was able to inhibit wide variety of gram-positive and gram-negative. Then in 1948, Abraham and Newton isolated three actives, that is cephalosporin, P1, cephalosporin N, and cephalosporin C. From the fungus, which is Cephalosporin acremonium. Then cephalosporin P1 is a steroid, had little activity on the bacteria. Then cephalosporin N, which was identified later that it is identical to penicillin N, has been used in clinical trials for treatment of typhoid fever. But it wasn't approved as a drug. Then cephalosporin C, which is a close conjugate to cephalosporin N, despite being active, but it had little potency on the bacteria. It had little potency. So they had to find a way to make other cephalosporins. Those are the synthetic cephalosporin. This one had low potency, despite being resistant to beta-lactamases produced by the Staphylococcus aureus, but had low potency than even the penicillin N and other penicillins. So cephalosporin C, this is its structure. It was mainly targeting the gram-negatives than gram-positive, especially the Salmonella species. So this side chain, it has the carboxyl group and amino group. So it's more of targeting gram-negative bacteria. So they identify that leaving this group and substitute other groups, they could synthesize other cephalosporins, which are more potent and active on both gram-positives and gram-negatives. So the general structure of cephalosporin, it is this. So this is the general structure. So this is the penicillin, this is the cephalosporin C. This is the general structure of the cephalosporins. These R groups mean that they can be changed or they can be modified to make other cephalosporins. This X, the X in cephalosporin, it can be a sulfur group, it can be a CH2 group, or it can be oxygen. It can be oxygen atom. So then this R4, the R4 can be hydrogen. In cephalosporins, this R4 is hydrogen. But if it can be methoxy group. If it's a methoxy group, meaning that one is a cephamycin. For cephamycin, it's a methoxy group. For cephalosporins, it's a hydrogen. This R1 mainly is responsible for the activity, the spectrum. The R4 mainly is for spectrum of activity, but again, it can participate in the pharmacokinetics. Then for R2 is mainly for pharmacokinetics, but again, it can participate in spectrum of activity. Then for R3, this R3 can be made as a salt, or it can be made as an ester. You can use this R, so it's also for pharmacokinetics. Again, this R1 and R2, they're responsible for steric hindrance against beta-lactamases, this R1 and R2. Then this cis form is very essential for activity of these cephalosporins. Now, let's go to nomenclature. Yes, for nomenclature, this is the genus structure of cephalosporins, and we said X can be sulfur, can be oxygen, or can be CH2 group. So, considering this structure, since most of the cephalosporins there is sulfur, I'm going to use sulfur as an atom there. So this ring 1, it is bicyclic. It is bicyclic, and it is 1, 2, 3, 4, 5, 6, 7, 8. So it is octane. Oh, it's octene. Oct2 in, because this is 1. Okay. This is 1, 2, 3, 4, 5, 6, 7, 8. Sometimes you may find that they come from the sulfur group. From here, 1, 2, 3, 4, 5, 6, 7, 8. But let me count from this side. So it is oct2 in, means that position 2 there is a double bond. Also, it has a carboxyl group. This one is a carboxyl group, so it is at position 2. So it has a 2 carboxylic acid. Then at position 8 there is oxyl group. So it has 8 oxyl group, meaning that nomenclature of this compound, if I'm to use this cephalosporin C, this is cephalosporin C. I can name the ring alone, then I can name these ones. Also, this ring, it is a 4 to 0. How does it come? This 4 is the number of atoms in the large structure. This 2, number of atoms is the smallest and the smaller ring. The number of atoms in the large ring, but which are not in the bridge. Yeah, here where there is fusion. So there are 1, 2, 3, 4. The number of atoms which are in the smaller ring is 1 and 2. Those ones, without these ones in the bridge. Then 0, meaning that the atom is fused, the rings are fused. So now for cephalosporin C, this one is astoxy methyl group. So it is astoxy methyl. Now this is an amino group. and this is the carboxyl group. Now, this chain, the side chain is 1 carbon, 2, 3, and 4, 5. So it is 1, 2, 3, 4, 5, means it's a pentane. Now we can name the structure. Alphabetically, we are going to start with this one. So it will be 3 acetoxymethyl. So now it will be now amine first before the carboxyl group. So at position, this is the position 7. Position 7, we have the side chain. So we say 7. Now at the side chain, we have the amine. It's at position 5 of the side chain. So it is 5 amino. Again, we have the carboxyl. So it is 5 carboxyl. This one is a pentane. So pentanyl. See on this amine group of the side chain. So it's pentyl, amine, amino. Now we come to this structure. Now we have 8 oxo. We have the 5 tire. We have 1 other. This is the tire group. This is the other group. Now it's a bicycle. So it is 1 tire, 5 tire, 1 other by cycle 4 2 0 4 2 0 octi 2 in 2 carboxylic acid. So that's our structure. Everything 2 carboxylic acid, we saw that it is a position 2. Now let's try this one. This is our cephalosporin. This is our cephalosporin, and it has this group. It is acetoxymethyl. This one, it is the thiophene. This one. So this is now thionyl group, and this is acetyl group. So we can name the structure. So it will be, let me use blue to differentiate from this one. So it will be 3 acetoxymethyl. Then at position 7, we have, so it is, this is 1 2. So it will be 2 thionyl acetyl, now amino. We have 8 oxo, 5 thia, this one, 1 other, this one, 1 other bicycle, to be 4 2 0. So it's on octane. So octane 2 in. There is a double bond here. There's a double bond, so it's oct2 in 2 carboxylic acid. So you're seeing, we try this one. This one, this structure is cephalosporins. This is cephalosporins. Okay, let me write it here. So it is cephalosporins. Our cephalosporin, we can name it. This one, this group is ethene. So it is ethenyl group. This group alone, it is thiazole. So it is 1, 2. It is 2. From this 1, 2, 3, 4, 5. So it is 2 amino. This amino group, and 1, 2, 3. So 2 amino, 1, 3 thiazole. So it will be thiazoyl. Then this is the position 4. 4, okay. It will be thiazole 4 aryl, because this bond is at position 4. Then when we come to this group is carboxy methoxy group. It's carboxy methoxy amino group. This one, and it's at position 1, 2. So it's at position 2. It is at position 2. Even this one is at position 2 of this side chain. This is 1 carbon, this is 2. And remember, this position is position 7 of the ring. 1, 2, 3, 4, 5, 6, 7. This is 8. Now, from alphabetically, we shall begin with this group. So, at position 7 of the side chain, so it will be 7. We have at position 2, there is 2. At position 2, there is 2 amino. 1, 3 thiazoyl, 2, 3 thiazole, 4 aryl, this position. Then there is 2 carboxy methoxy amino, this group. Then this group is acyl. It is on this side chain of the amine, so it will be acyl amino. Then now we come to this group is 3 ethynyl. So 3 ethynyl. Then we come to 8 oxo, 5 thia, one other bicycle 420 oct 2 in, then 2 carboxylic acid. So that's how we name cephalosporins. That's how we name our cephalosporins. Now, going to semi-synthetic derivatives, having found that cephalosporin C was highly targeting gram negatives than gram positives, so it had can send now spectrum because it was targeting few gram positives but high gram negatives. They found that this group could be cleaved to synthesize other cephalosporins, and this group, it's the highly living group. So meaning that cephalosporin C was parental, mainly parental, because of this living group can't withstand the GIT acidity. So it had first, it had low potency because it is highly lipophilic. Then it was parental, mainly parental, so they had to get alternatives to make oral cephalosporins. Then also it was mainly for gram negatives. Mainly for gram negatives. So, for example, this synthetic derivative, this is the natural penicillin, cephalosporin, this is the synthetic cephalosporin. Now, they cleave this group, so they got the acid from this amino group, so they substituted with this thionyl acetyl group. So, it's more of lipophilic than hydrophilic, meaning that this one can target more gram positives. So, these cephalosporins for gram positives and gram negative, so it has a wider spectrum of activity. But there is also a problem of this leaving group, that it can be cleaved by esterases and also by the acidity of the GIT. So they continue to make other cephalosporins. Another example is this cephikism. Cephikism, they substituted this group with amino thiazole. This group, then they also put another group, this group, and also change this living group into non-living group. Living, this group is living, can easily be cleaved, but this one is not easy. So this one is responsible for oral availability, meaning that it can be administered orally. So this cephikism is an oral cephalosporin, but this one, it is a parental, as cephalosporin was parental. Now, all other cephalosporins, so they change this R2 and R1. Mainly, the substitution is at R2 and R1. Now, let's see the chemical degradation, how this group is cleaved, how this one can be also cleaved. Yeah, mainly. For chemical degradation, various cephalosporins undergo various chemical degradation depending on the structure. Those with acetoxyl methyl derivative, as we saw them, mostly they undergo this road where this R group is replaced by a nucleophile. For example, OH group, they are replaced by a nucleophile. So shall get shall get this. Where our group is replaced by a nucleophile. Now, forming this structure will undergo lactonation by the presence of acid to undergo lactonation where we lose water. That's why most cephalosporins with a good living group like acetoxate, methyl group, they are not given orally because they are degraded by the acid. So we shall form this. So that group is lost as water. So we shall have a lacton ring. So we shall have a lacton ring. So this compound is inactive, meaning cephalosporin can be degraded by this mechanism. Then they can be degraded by acylation of this group. Remove the acyl group. So here, the acylation by acylases, so we shall undergo hydrolysis, where we form this group, this compound. R may not be touched, it may remain. Then you form NH2. The acyl group is cleaved. So this one is by acylases. So this compound formed in presence of acid, we shall lose water, we can form the same structure, but with no acyl group. So it will be there is a bond, there is a double bond. Even here, it's there. Meaning here we shall form a lacton ring. So after forming this compound, meaning that the cephalosporin is inactivated. So this compound is inactive. This one is 7-amino cephalosporanic acid. This one is the acetyl. We have removed the acetyl group. Then it is the acetyl 7-amino cephalosporanic acid. So we have removed this group. So it is the acetyl. Then for this one, it is this one is cephalosporanic. It is the acetyl. Cephalosporin, lactone. Then this one is the Cephalosporin. Now this one is a lactam, this one just the Cephalosporin. Then again, these cephalosporins, they are also inactivated by beta-lactamases. By the beta-lactamases. So it can be the OH, or you can say deoxynium. So as you saw in penicillins. Now, remember, for beta-lactamases, they cleave the beta-lactam ring. So we shall form this. This ring will break, so we shall form this. So the R group may remain untouched, but sometimes even R group can be lost for those ones with a leaving group. For example, methyl group. So for methyl groups, we shall form this R. We shall form this compound. For them, when the enzyme attacks, this one represents the enzyme binding site. Instead, these electrons, instead of attacking the proton, they will be used to form a bond here instead of getting the proton. Because at first there was no proton. We use these electrons to get a proton. So it is S. So when this one uses electrons to form a bond here, meaning that, okay, let me do this mechanism. Remember, as the ring breaks, so at first the ring was that. Was like this. When this enzyme attack this carbon, electrons will come to oxygen, but again they will come back. When they come back, this one will have excess bonds, so this ring will break. On breaking, these electrons, instead of getting the proton, now they will be used to form a bond here. Remember, you had a bond, you have a bond here. Then when you form a bond here, this carbon will have excess bonds, so this one will form a bond here, then this one will break off, meaning that we shall have our cephalosporin like this. Shall have a cephalosporin like this with a double bond here. Now also double bond there. This one has broken off, so here we have a carboxyl group. So this one will be inactivated. So that's how cephalosporins are degraded. One, by replacement of this acetyl group, and it's the most reactive part for those methyl derivatives. Then can be degraded by acylases and can be degraded by beta-lactamases. So please, if you want to see how really this mechanism works, how we break the beta-lactam ring, please go and watch the penicillin part 1. Yeah, we discussed this mechanism. It's the same mechanism which works here when the beta-lactamases degrade this beta-lactam ring. Now, for oral cephalosporins and parenteral cephalosporins, let me discuss them at once.